Okay, so a set can be an infinite or a finite collection of items. So basically, whenever we have a set, what we're going to think of is a bunch of items collected into a set of something. A finite set means a set that has a specific number. So if we have a finite set, it's going to have a specific number of elements inside that set. If we have an infinite set, then that list will continue on forever. There'll be a bunch of different elements, and we can't necessarily count how many elements are in that set. So we have both finite and infinite sets. Set builder notations allows us to symbolically represent a set. So for example, what we're going to see is we're going to see different sets. So we're going to see them kind of in this notation. And basically what this tells us is that we have a set S. So we have a set S, which has elements X. So we have elements X, where X meets these specific conditions. So set S will have X's that meet these specific conditions. And so we'll go ahead and label out what those conditions are depending on what kind of sets we have or what kind of elements in those sets that we have. But we represent them like this. So S will tell us, basically just name that set. But what we're really going to look at is what conditions do we have for the elements in that set? What conditions are they meeting? So, for example, let's look at this set. We have this set of integers, and this is an infinite set. We know this is an infinite set because they continue on forever. That's what those little dots mean, that it continues on forever, right? We can't account for every single number in that set. And so here we have two sets of infinite sets. Well, we can go ahead and represent this set as a specific set notation. So I can put set S. So I have a specific set S where every X or every element is a number. Right? All my elements in my sets are numbers. I have -2, -1, 0, 1, 2, 0, plus -1, plus -2, right? All those sets, all those different elements in this set, we're looking at these sets right here, they're numbers. So we can say that this set, what we have here, every X in it or every element X is a number. So that's how we can go ahead and represent this set. So basically we use this set notation to represent the conditions that these elements, all these different X values stay in. And so they're all numbers, and so we can say that they're all numbers. Okay, questions about this? Okay. So now we're going to look at different components of sets. So again, a set is a collection of items. They can be objects, they can be people, they can be numbers. Whatever we want to include in our set, we definitely can. The different things that we see in our sets, for example, here we saw different numbers. Each of those different numbers is called an element. So an element is an item in a set. So basically what is contained in that set, what we see in that list of numbers, every number would be an element. Okay. There is a symbol, and the symbol looks like this. It looks like an E, identifies an element of a given set. So basically if we see something, for example, if I see three E S, what that tells me is 3 is included in my set, and right, 3 is right there. So it is included in my set of numbers. So 3 would be included in my set. So this number, this symbol E, just tells me that that element is included in my set. Okay. This symbol, however, where we have E with a slash through it, tells me that that number is not included in my set. So for example, if I wanted to write -5, -5 is nowhere in this set. And yes, my set does continue on forever, but it does so in the positive way. So we would have 5, 6, 7, 8, right? It would never contain a negative number because it continues forever in the positive direction. And so because of that, -5 would not be included in my set. And so this symbol would tell me that element would never be included in my set. It's not included in my set. Okay, so again, this symbol that just contains this E. This E tells me that 3 is included in my set. And because my set here is named S, that's why I write S here. So 3 is included in my set named S. That's what that's telling me right there. Here, what this is telling me is -5 is not included in my set named S. That's what this symbol right here, that's the S. So if I want to describe the different elements in my set, what I can use are these different symbols. The E by itself would tell me that that element is included. An E with a dash through it tells me that that element is not included in my set. Okay, questions about this symbol? Questions, concerns? No? Okay. So now we're going to look at other symbols. Again, today's just trying to identify these different symbols and how they relate to different sets and different elements. So we have a symbol which represents a universal set, which is U. We would use a capital U to represent a universal set. A universal set is basically a set that contains all the elements under that condition. So for example, a universal set may be a set of numbers. There's a bunch of different numbers. We have positive numbers. We have negative numbers. Universal set just contains all the different elements under all the different conditions. Okay. We also have a symbol that looks like this, where it's a circle through a dash like it. That represents an empty set. That means that there's no elements that we can think of that would fit into that set. So this is our universal set, empty set, which means there's no element that would fit those conditions. We also have A, or this symbol right here, which tells me that I have a subset. So this would say A is a subset of B. Basically, that means if I have symbols that are listed under my set A, they would also be listed under my set B. So every element in set A would also be in set B. So whenever we see that symbol right there, that symbol means a subset. And so that means every condition for A would also apply for B. And we'll look at some examples of that. Lastly, we have this symbol right here. What we're looking at is this exponent C on the top of a set. What that tells me is that I have a complement of a set. So if I have something that's a complement of a set, what it's basically telling me is there are elements that cannot exist in my set. So things that are not included in my set is basically what my complement would be. So my complements would be things that are not included in my set. So it's not included. Okay, so these are the different symbols that we're going to come across. We're going to come across the universal set, the empty set, the subset, and the complements of set. And these are the symbols that we use, but we'll look at an example of them right now. So here we have an example. Here we have different types of sets, and what we're going to look at is how we can represent different sets using those symbols. So if I had something that looked like this, what I notice is I have this symbol right here. What I'm going to need to be able to do is to be able to identify what is that symbol telling me about the relationship between those two sets. What I know is this symbol, we just looked at it, it represents a subset. And so basically what that tells me is, we'll look at it right now. So C is a Sunnydale senior who plays football. So Sunnydale senior plays football. That's what my set C represents. So it basically represents all the Sunnydale seniors who play football. A would represent the Sunnydale juniors or seniors. So Sunnydale juniors or seniors. What this is basically telling me, what this subset is telling me, is that everything in my set A, all my Sunnydale seniors or juniors are included in my subset C. So the way that I would say that is the Sunnydale seniors who play football are also, that's my subset, are also in the set of juniors and seniors who play, are also in the set of Sunnydale juniors and seniors. That's basically what this expression is telling me. So C would represent my Sunnydale seniors who play football. This subset I'll represent by this green, so are also, and then A, I'll color code it as red. So basically that is what my subset is telling me, or what that symbol is telling me. I did not mean to do that. Let's see. So basically when I have a subset, what it's telling me is that those two sets, my C set and my A set, have a relationship. And this is the relationship that it's telling me. It's telling me my Sunnydale seniors who play football are also the Sunnydale juniors and seniors. So basically there's no unique seniors who just play football. Those seniors who play football are also going to be part of the set of Sunnydale juniors and seniors. Okay, so that's how we represent subset. However, if we saw a symbol that looked like this, we have the symbol there for complement. This is a complement. Remember that the complement includes everything not included in that set? Hi. So again, A represents my, bye. A represents my Sunnydale juniors and seniors. B represents my Sunnydale freshmen and sophomores. Why did I write it like that? Right, and I'm getting this information from what my set tells me about those things. So B here, it says Sunnydale freshmen and seniors. So basically what I need to be able to do is understand what a complement means. The complement basically tells me that the relationship does not exist between those two. So I would say that the Sunnydale juniors and seniors do not include the Sunnydale freshmen and sophomores. So are not also the Sunnydale freshmen and sophomores. So that tells me that this symbol right here represents or also. It means that those two have a relationship to each other. So C has a relationship to A has a relationship to C. What this italicized or exponent C tells me is that there's no relationship between those two sets. So those two do not exist. And so that's how we would explain or represent these different relationships. Mm-hmm. We can also represent sets in Venn diagrams like you see here. Like you see here. A Venn diagram is basically just a graphic organizer representing the relationships among groups of sets. So we can represent our sets like we saw before as these sentences and then use these symbols to represent the relationships between these sets. Or we can use a Venn diagram to represent the relationships between these sets. So whenever we have a union, we'll represent that using this symbol right here, which looks like a small u, a lowercase u, okay? So if I wanted to find the union, so of A, union B, what that union tells me is it's everything in the set, including everything in A and everything in B. So my union would represent everything in A and everything in B. My unions represent everything in A, everything in B. So this shaded regions would represent that union between A and B. So if I have a union, all the elements of either sets or both sets will be included. Okay, so that whole shaded part. I also have what is known as an intersection. An intersection is represented with a upside down U, and intersections only represent the things that they have in common. So that means the center part. This center part would represent the intersection between A and B. So that's intersection means what they have in common. A union represents everything in A and everything in B. An intersection only represents what they have in common. So that centerpiece. Okay, questions about this? So union, a small lowercase u, and intersection, a small upside down u. Okay. So here is an example. Here we have our universal set. So this is basically all the elements included in my set. So universal set means all the elements included in my set. Everything in A is going to be an even integer, so all my even numbers. Everything is B is going to be all my numbers that are divisible by 3, so divided by 3. So first thing I'm going to look for is all my even numbers. Negative 14, 2, 12, 24. Those are all my even numbers, so I can write those in here. Negative 14, 2, 12, 24. Okay. Now I'm going to go ahead and look for those numbers which are divisible by 3. So I can divide them by 3. Negative 9, negative 3. I can actually do that by 12 and 24. So I have an overlap, 12 and 24. That means I can go ahead and move those in the center, because those apply for both. 12 and 24 are both even numbers, and they're both divisible by 3. And then I can write my other numbers right here. Well, what you'll see is I also have numbers which are not included, which are not being highlighted. And so I would just put those on the outside. Anywhere on the outside is fine. Okay, so what I've done is I've taken my universal set. Remember, my universal set means all of my possible all elements available. So I've taken all my universal sets and I've divided them into A, values that are even numbers or even integers, even numbers, and values that are B, divisible by 3. And then I've put them into this diagram. So in A, I have all my even numbers. In B, I have all my numbers divisible by 3. In the center, I have all my even numbers, which are also divisible by 3. And then on the outside, I have all those extra numbers that I have. Okay? What I can actually do here is I can represent now my union and my intersection. Let's start with intersection. Remember that intersections are only the numbers that are contained in the center. I only have 2 numbers contained in the center, 12 and 24. So that would represent my intersection point. Okay. Now, what about my union? We know that my union is all my numbers in A and all my numbers in B. So I can write all those numbers out. 14, 2, 12, 24, negative 9, negative 3, and 15. Right? Those are all my different numbers included in both of those parts, both in my A and my B. So using these symbols, what I can do is represent my union and my intersection. Union is everything in A and B, including the intersection, and my intersection is just that center part. So basically, I'm using this information to create a diagram that represents these different sets, and then using that diagram to kind of just represent, okay, what elements, what different numbers fit into these different intersection points. Any questions about this? Okay, the last thing we're going to do is look at how we can go ahead and use this information and use these diagrams to kind of represent what is included in my sets. So A, Well, when I'm looking at A, what I notice is A is this blue circle right here. So I want to identify what number would represent my subset A. Well, A is this entire blue diagram right there. So that means I would include every number that's in A. 6, 8, 3, 5. And so 6, 8, 3, and 5. All those would represent my elements of A. And because here I'm looking at the number of students who are taking geometry, basically what it's telling me is I have 6 students, 8 students, 3 students, and 5 students. If I add those together, I have a total of 22 students who are taking geometry, according to this diagram. Okay, so that's for A. Now for B, I'm going to look at this circle right here. So all of these different students in that circle right there are taking biology. I have 10, 3, and 5 students. So 10 plus 3 plus 5 students. I have 18 kids who are taking biology. So what I'm doing is I'm using this diagram to kind of use these different numbers to explain how many elements are in my set. How many total elements are in my set? How about C? We'll see, I notice I have 2 numbers in there. I have 5 and I have 14. So 5 plus 14. That tells me I have a total of 19 students taking literature. And then lastly, I want to look at D. D only has this small number right here, which is 6. And so that tells me that 6 kids are in the math club. Okay, so what I'm doing here is I'm using this Venn diagram, looking at all my different sets. And these sets will basically tell me what conditions do those elements in that set tell me. What conditions do the elements in that set follow? And so basically all of the numbers or all of the variables or elements inside of that set would represent all of the elements X which follow whatever condition that set tells me. So all these kids here, there's 6 kids and there's 8 kids and there's 3 kids and there's 5 kids. Well, because they all fall into set A, that tells me that all those kids take geometry because that's my condition. With B, there's 3 kids, there's 5 kids, there's 10 kids. Well, they're all included in that set B. All those kids in set B take biology. And so I'm using this Venn diagram to, in this instance, calculate how many kids take these different classes. But this Venn diagram also tells me how many kids follow that condition. How many kids take geometry, how many kids take biology, how many kids take literature, how many kids take math. Okay. And here's just kind of an overview of this. You can kind of see here, they're trying to find an ice cream company working on new flavors, have 50 people test the new creations. They are then asked to pick their favorite flavors. The results are in the Venn diagram. So from this Venn diagram, we can kind of get an understanding of how many people picked each different types of flavors. And here's all the different combinations that we can assume from that Venn diagram using that information. And so basically what this is just showing you is that you can use these Venn diagrams to calculate information about the similarities between sets individually, and kind of just make determinations about that. So for example, 5 people liked both banana cream pie and pineapple upside down cake. That is represented by this number right here. So I could determine that from this Venn diagram. So you can make all these different conclusions from these Venn diagrams about the relationships between these different sets, the relationships between these 3 different types of flavors that they tried out. Okay. So that's what we're going to be able to do as we progress through this unit. Okay. So what the takeaway is today specifically is to be able to understand these different types of symbols. So we looked at different types of symbols, and these different symbols tell us different things about the sets. We have our universal set, which is represented by a capital U. We have a union set, which is represented by a small u, and a B. This small u represents our union. We have an intersection of a set. Whenever we want to represent an intersection of a set, we use this upside down U. Whenever we want to represent a subset, we use a sideways U. Whenever we want to represent a complement, we use an italicized C or a exponent C. And whenever we want to represent an empty set, we use a circle with a line through it. So all these different symbols are going to eventually allow us to interpret different diagrams. But right now, basically what you want to take is, how do I represent universal sets? How do I represent unions? How do I represent intersections? How do I represent subsets, complements, empty sets? Oh, and what does set notation tell me? Set notation tells me I have a certain set. You can name it whatever, A, B, C, whatever you want. But basically what this set will tell me is, what criteria does my elements have to meet in order to be part of that set? Do they all have to be numbers? Do they all have to be letters? Do they all have to be even numbers, etc.? Okay. So if I was going to take some time to review this today, I would try to go ahead and memorize these different symbols, because using these different symbols, we'll be able to interpret different Venn diagrams and different sets and their relationships with each other. Okay, but we'll go over those example problems tomorrow. Questions? Okay. If there's no other questions, you guys may log off, and I will see you guys tomorrow. Bye, guys.